is Alexis Conley, and I am Bridgewater class of 99 and MBA 14, and I am the Assistant Director of Alumni Relations at Bridgewater State University. On behalf of our office, I would like to welcome you to our virtual Aluminar series. Today's presentation, The Science and Adventure of Solar Eclipses, a discussion with Dr. Martina Arndt, Professor of Physics at BSU. Before we begin, there are a few important housekeeping items that I'd like to address in order to make this a great Zoom experience for everyone involved. First and foremost, I must mention that this presentation will be recorded for future use. In the top right corner of your screen, you will see two viewing options, full screen and speaker view. We suggest the speaker view for optimal viewing. Throughout the presentation, please keep your own screen muted and with the video off at all times as to not distract from our presentation. Q&A will take place immediately following the talk. Please feel free to type in questions at any time during the presentation using the chat feature in the middle of your bottom toolbar. Questions will be collected and answered at the end. We thank you for your attention to these guidelines, and it is with great pleasure that I'd like to introduce you to our guest host, Robert Bradley. Rob Bradley is head of Bridge Research at State Street Associates, a team that bridges the gap between empirical finance research and practice. He is co-chair of the Bridgewater State University Employee Network at State Street and is on the board of State Street's Numerates Network. He is also a part-time faculty member at Boston College and Northeastern University. He holds a bachelor's degree in economics from Bridgewater State University, class of 2012, where he also majored in English, a master's degree in applied economics from Northeastern University, class of 14, and is a PhD candidate in applied economics at Northeastern, class of 2020. Rob lives in Bridgewater with his wife and 3 sons. Take it away, Rob.
Thank you, Alexis. Welcome back, everybody. And for those of you, if this is your first Aluminar, welcome. So today we have an excellent presentation. I'm really excited about this one. So Dr. Martina Arndt is the Interim Associate Dean of the Bartlett College of Science and Mathematics, and as Alexis said, a Professor of Physics. She earned her BA in Astronomy from Wellesley College, class of 91, and her Master's and PhD in Physics from the University of New Hampshire, classes of 97 and 20. She's currently working on her MBA at BSU and expects to graduate in the spring of 22. Since 1997, she's been part of the Solar Wind SHERPAS, a research team that travels the world to gather data from total solar eclipses. To date, she has observed 12. She also works with students on exoplanet research and is BSU's representative in NASA's Massachusetts Space Grant Consortium. She's a co-investigator on multiple National Science Foundation grants totaling over $300,000 that have supported research activities on eclipses as well as women in STEM. Since joining the physics faculty at BSU in 2000, she's worn many hats, including professor, mentor, chair of physics, and my former haunt, economics. She is student and co-coordinator for the Center for the Advancement of Research and Scholarship, CARS. She's now serving as the Interim Associate Dean for the Bartlett College of Science and Mathematics. Dr. Arndt, her husband, their 15-year-old daughter, and 1-year-old Cavachon puppy live in Grafton, Massachusetts. So without further ado, please take it away, Dr. Arndt.
Oh, thank you so much for that nice introduction, Rob. And thank you, Alexis and Kelly, as well, for all of your help with organizing this, this webinar, and also for even inviting me. I'm thrilled to be here because I get to talk about one of my favorite things, which is total solar eclipses. And I think it's always really important to start these things off acknowledging that I couldn't do any of this work without support from the National Science Foundation, from Bridgewater State University, from the Institute for Astronomy at the University of Hawaii, and from NASA. The work that we do is expensive, but it's not nearly as expensive as, let's say, launching rockets. So it's amazing what kind of science you can do even with just a little bit of support. So, okay. I like to talk about how my journey started. And what I'm going to do is talk to you a little bit about my path on how I got to Bridgewater and doing this work. I'm going to teach you a little science because that's just who I am, and then share with you some of the adventures, right, of total solar eclipses. And so I always like to think that my love for astronomy might have started when my mom rented a television back in 1969 so that we could watch the moon launch. And I was only 4 months old, and this is not a real picture of my family, but mom always likes to take a little bit of credit for that, and I'm totally fine with that. But the first memory I do have about loving astronomy came when I was around 11 years old and watched the series on TV called Cosmos. And at that time it was with Carl Sagan. And I remember sitting and watching the TV and, couldn't be recorded. You have to watch it real time, right? And hearing about billions and billions of stars. And it was always sort of a fun thing to think about. And the newer generation, those of you who might be younger, in the audience, right, might know of Neil deGrasse Tyson's version of Cosmos that came out in 2016, but it definitely made a big impact on me. And as Rob mentioned, I went to Wellesley College and I graduated in 1991. I grew up in Newton and I didn't go very far. I went to Wellesley. And it's a liberal arts institution, right? And I went in wanting to be a math and a German major, and then I switched my majors multiple times. But then I had to take one of those lab sciences, those things that we make our students take. And I didn't want to do chemistry or physics, heavens, no physics, no biology or anything. I was like, all right, I'll take an easy lab science. So I took astronomy, and wouldn't you know it, I just fell in love with it. And so I mentioned to one of the professors that, I really enjoyed the class. Was there another one that I could take? And she says, oh, great, you want to major in astronomy? And then I was off to the races. Wellesley has multiple telescopes, and this is one of the older telescopes here on the right. And one of the things that we would do is we would put cameras on the back of the telescopes and take pictures. And I will never forget the first time I ever looked through one of these telescopes and saw Saturn. This is not a picture that I took through the telescope, but I remember it looking just like this, seeing Saturn through the telescope, and I couldn't believe that I was actually seeing the rings and that I could actually see the gap between the planet and the rings. And I thought someone had taped a picture on the end of the telescope, and they hadn't. And I realized that I could kind of mesh two things that I really enjoyed, which was photography and also the astronomy part. So that was my first wow moment. But I will tell you, and maybe some of you in the audience might resonate with this, but after my undergrad, I was pretty burnt out. I wasn't quite ready to do graduate school or anything else. I didn't know what I wanted to do. And so I was very fortunate that this woman, Dr. Shadia Rifai Habal, she hired me straight out of undergrad to work with her as a research assistant at the Harvard-Smithsonian Center for Astrophysics. And that's in Cambridge, Massachusetts. So again, not going too far. And it was with her that I learned about the sun and grew to fall in love with the sun, actually, in part because she showed me pictures here of the sun from Skylab, and some of you in the audience might remember Skylab when it was sort of a big deal in the 70s. And this picture just captured my attention. And one of the things that she taught me was that she had brought in some of my classmates with me for the job interview for this research assistant position. And I didn't have the highest GPA. I didn't play sports. I didn't have a lot of the extra stuff. But when she and I were talking, she later told me that she really appreciated that I was a creative person, and she felt that my creativity set me above the other students. And I like to tell that to people because I think being a scientist, you might have an image of a scientist being a very linear, math only person, but creativity is a really important part of doing science. And I think in many jobs, because it helps you think about different things. But I tell you this too, because you're going to see Shadia many times throughout this whole presentation, and I wanted to acknowledge her impact on my career and my life as a scientist. But in my 2 years there, I decided I was ready to go to graduate school. And so I applied to and was accepted to the University of New Hampshire, where I studied for 7 years a solar flare that happened on November 15th of 1991. So if you think about it, that's right when I had first started working with Shadia, right, in 1991. And what we did is as I was studying this flare that lasted 5 minutes and took 7 years to try and figure out, right, using data from the Compton Gamma Ray Observatory and observatories from around the world, actually. So I have one of the most full color pictures of this solar flare. And it was at the University of New Hampshire. A couple important things happened. I got to observe my first 2 solar eclipses with Shadia, and I went on a blind date with this guy over here named Rob. And right out of, and you'll see him again later in this whole thing. But you know, when I graduated UNH, one of the things that you can do as a physicist is do a postdoc, you can go work in industry, or you can become a faculty member. And I realized when I was at UNH that I really, really loved teaching. And I was very fortunate that Bridgewater State College at the time, right, had some openings in the physics department. And Dr. Tinsley, who I think is on this call today, was president at the time. And I remember meeting her and being totally gobsmacked. And you'll also hear her name again later on in the presentation. But I started at Bridgewater straight out of graduate school, and I've been here ever since. And I like to say it's the best job I've actually ever had. And during that time, right, I decided to marry that guy, Rob, and we decided to have a kid named Haley, and she's now 15 years old, and you'll see her come up again. And since I've been at Bridgewater, I have observed 10 solar eclipses, and I can now add, as Rob mentioned, I'm finishing up my MBA in the spring, and I'm going to get it in 21 instead of 22. Being online actually allowed me to double up on my classes this year, so I can get done a year earlier. So it turns out that Rob and I are a perfect match because he's also a bit of a geek, and we did get married in 2003. We thought it would be smart because we had just bought a house together, and we had, on our wedding cake, we had equations. You should be able to see some of them here. PV equals nRT, and the sum of the forces equals MA. So that was perfect. But, you know, we decided to get married on November 15th, right? Which was also the date of the anniversary, if you will, of the solar flare that I studied. So, and then for our honeymoon, we went to see a rocket launch. So truly, match made in heaven, I'm telling you. So anyway, being at Bridgewater has been a really, really great experience, and I feel very fortunate to be here. So that's the path that I took to get here. I did not know, I'll let you stare at this beautiful video for a minute. I did not know that this is what I would end up doing when I grew up, right? I had applied to one college as an undergrad and I got in. I was only accepted to one graduate school, and that's where I went. I applied to a couple faculty positions, but you know, Bridgewater snatched me up, and that's sort of been the path I've taken. And you'll notice that I haven't left much of New England in this time, right? But you'll see that I have made up for that in other ways. So let me get you an introduction to the sun, all right? The sun is our closest star, which, by the way, I got wrong on my first astronomy test in college. I argued with the professor who ended up recruiting me. I argued, I said, no, you know, Alpha Centauri is the closest star, because I guess I don't know what I thought the sun was, but I didn't think of it as a star because it wasn't up at night. But now you will not get that question wrong should you ever take an astronomy class. But the sun is our closest star, and it's very dynamic. And this is a video taken of the sun yesterday. You should notice the date at the bottom. It says 11/17. And let me orient you a little bit on this star of ours. You could fit 110 Earths across the middle, so to give you a sense of scale. You'll notice it's rotating a little bit, and it takes about 27 days or so for this to rotate all the way around once. You'll notice some look like little loops and beautiful regions here. The sun has, those are actually part of a sunspot region. And you see what's this outer surface here. And actually, Alexis, or Rob, can I interject? Can you see my mouse when I move it? Can I just ask you that?
Yes, we can.
Okay, good. Thank you very much. So you'll see that this outer circle here is what I'm going to call the surface of the sun, but it's not really a place you want to stand, okay? But that's that round orb that you see at sunrise or sunset. You know, the roundish part, but it's a ball made of plasma, right? So it's not solid. But I want you to think about that as the surface, and then above that surface, right, is an atmosphere, and you're going to learn more about this atmosphere. These videos, by the way, are online. I could tell you how to find it later, but I often make Christmas cards or holiday cards or anniversary cards with a picture of the sun on the day that someone was born or whatever. That can be really fun. But all of these data are publicly available. And it's sometimes just really nice to look at. So this plasma that you're looking at right now is about 1.1 million degrees Fahrenheit. It's very, very hot. And also just keep in mind that you got stuff moving here and that there's some features in the upper atmosphere. There are actually magnetic field lines, and they move and they change shape. So what I'm going to do now is take a cleaver and cut the sun in half. Okay. Remember, 110 Earths across the whole thing. And at the center of the sun is the core, and that's where hydrogen gets fused into helium, and you get lots of energy that comes out in the form of light, which makes the star shine in the first place. Okay. And then there's a few more regions in here, but the surface that we were talking about, right, is called the photosphere. And then the upper atmosphere of the sun that I was talking about, the part that looked like it had little magnetic field lines and things, we call that the corona. And there's actually a reason why we call that the corona, because during an eclipse, when you see this atmosphere, right, it looks like a crown. So think of coronation. It's like a crown around the sun. The problem, though, is that this corona is 1,000 times fainter than the surface of the sun. So we can't see the corona unless we block out this photosphere. And that's one of the reasons why eclipses are important. But one of the neat things about the photosphere, right, is that it's about 10,000 degrees Fahrenheit. That's pretty hot. But when you look at the corona, it can go up to like millions of degrees Fahrenheit. And I want you to ponder that for a second. If you are close to something that is hot, and then you move away from this thing that is hot, you would expect to cool off, right? But it turns out that on the sun, when you move away from the surface of the sun, you actually get hotter. And that, my friends, is called the coronal heating problem. We don't understand yet why the corona is actually hotter than the surface of the sun. We know it's much less dense, so that sort of takes away some of that effect, because it's like, you know, if you have one droplet of scalding hot water versus being in a shower of it, it's different. If the density is lower, the impact is different. But I mention this because this is one of the problems we're trying to solve in solar physics. It's almost a bit of a holy grail, right, about why the corona is so much hotter than the surface. The other thing that we study with the sun is that the sun is constantly sending out particles away from the sun into space. And we call this stream of particles the solar wind. So if you blow on your hand, right, you can feel particles hitting your hand, and the particles are coming from you. The sun is spewing out particles and sending them out into space. And what that does, right, is it interacts with the Earth's atmosphere and the Earth's magnetic field, and we get the northern lights and the southern lights. And if we were in a room together, I'd ask how many people had seen these. I've seen them once, and they're quite beautiful. I will say that pictures often capture it better than seeing it in real life. But what's interesting is the solar wind sends these charged particles to the Earth. They migrate down through the Earth's magnetic field. They hit the Earth's atmosphere, and they interact with the molecules in the Earth's atmosphere. And in this case, we see the ones that emit green, and I think that might be oxygen. And I like to include this slide just as a side note, because astronomy is one of those things that is accessible to a lot of people. You know, people look up and they see stars and they find them interesting, or they can travel to Iceland and go see the northern lights and take pictures. Lots of amateurs can engage in this kind of work. And it turns out that a bunch of amateur astronomers who loved taking pictures of the northern lights started to notice this purplish color that no one really had ever talked about before. And it turns out they're the first ones to really pay attention to it. So they got to name it, and they got to name it Steve, actually. And that's actually how it shows up in the literature as what it's called. And it's currently being studied as to why we see this pinkish purplish color in the northern lights. But I don't want to digress too far down that path. I showed this intentionally to talk about how the sun affects us and why we want to study it, not just because it's cool to understand this interesting coronal heating problem, but, you know, it interacts with the Earth through the northern lights, but also in other ways, right? Climate change, it plays a role in climate change, as do humans. We get a lot of energy from the sun. Many people have these solar panels and they're harnessing this free energy, truly, right? And it's going to be giving us this energy for another couple billion years. So it might be smart to figure out how to use it. You know, we have to wear our sunscreen, right? So that we don't get burnt by the sun. And also we need the sun to help us grow all of our food. So in many ways, there are practical reasons to understand why the sun does what it does, in addition to just the scientific fascination with some of the puzzles that it presents us. So let me delve then into eclipses a little bit and give you a tutorial on total solar eclipses, okay? And I do this in part so we have the same vocabulary while we're talking, or while you're listening and while I'm talking. And I want to also point out that this picture is not to scale, okay? The sun is remember, it's 110 Earth. This one looks like the Earth is bigger. But here's the sun, here's the moon, and here's the Earth. And it has to be in that order for a total solar eclipse. And what happens is the sun is so large that it casts a shadow from the moon onto the Earth in this direction and in this direction. And when those two shadows overlap, you get a true little dark spot where you can stand and you can see the moon completely covering the sun. And standing in that dark spot is called the umbra, and that's where you see the total eclipse. The part where it's lightly gray is where one of the shadows doesn't overlap the other one. That's called the penumbra. That's another word you'll hear. And that's where you stand to see a partial eclipse, where you won't see the sun completely covered by the moon. The only way you can see that corona and that upper atmosphere of the sun is if you stand in this umbra right here, and that spot is only about 75 miles wide on average. And you'll notice, right, that you have to stand in that spot. If you're standing over here, you're going to be completely out of luck. If we're in Bridgewater, you're completely out of luck. You've got to stand right in that spot. So the eclipses force me to travel the world, which isn't a bad thing. One other thing to note with solar eclipses is that the moon, right, sometimes is closer to us, and we call that perigee, so it looks bigger. And sometimes it's farther away from us, and we call that apogee when it looks smaller. And it turns out that when the moon is in apogee and it's right in front of the sun, it does not block the whole thing. You have to have the sun at perigee, at its closest point, in between the sun and the Earth, to be able to see a total solar eclipse. So sometimes people say that total solar eclipses are rare. I would argue that you see them about once every 18 months. That's not completely rare, but you know, they in theory should be happening more frequently, but they don't. So it's a significant and special enough event that you kind of, when it happens, you need to go see it. When the moon is closest, right, this is just a visual representation of what I've just said. So let's think of this as a summary. When the moon is closer to us, right, it looks larger and it covers the whole sun, and we see the upper atmosphere of the sun. When it's further away from us, it doesn't do as good of a job covering up the sun, and you end up with this little ring right here. We call it an annular eclipse because it looks like an annulus. And when you are in the penumbra, right here, you'll only see a partial eclipse, which is what this looks like right here. So this is a summary of the different kinds of solar eclipses. The kinds that I care about and the scientists tend to care about are the total eclipses. So here's a chance for audience participation, and Rob or Alexis is going to help me with this. Would you please answer if you have ever seen a solar eclipse? And if you don't know, put no. Ooh, we have a lot of people who've seen them. Let's wait another second or so. But look at this. It looks like that a majority of folks have actually seen a solar eclipse. And I wish, you know what, I should have asked if you have seen a total or a partial, but I'm going to end the polling. And I'm going to share the results, which apparently I can do. So it looks like 13 out of 19 of you have seen one and 6 have not. And hopefully by the end of this talk, I will have convinced you that you need to go see one, okay? And I will share with you ways that you can do that. Okay, so I'm going to close this. And I think one of the reasons why so many of you maybe have seen a solar eclipse is possibly you were able to partake in the Great American Eclipse of August 21st, 2017. In Bridgewater, we had, I think, 1,600 people at the science building and at the observatory standing outside with these special glasses on, right? Because looking at the sun is bad without eye protection. And what they would have seen is something like this over here, where the sun is partially covered. It turns out so one safe way to look at a solar eclipse is with these glasses. Another is through a pinhole camera, which this is a high-tech version of a pinhole camera where the light comes in through a pinhole, but you can use a cracker, actually. You can use a sieve right here, like when you strain your pasta. This is all little mini partial solar eclipses in here. So I'm guessing the numbers are high in part, and maybe in the question and answer session, folks can share with me if they actually traveled perhaps to even see the total solar eclipse. But most people, I think, in the United States have at least seen a partial eclipse, which is very fortunate. So, okay, me, the New England gal, right? I have seen 12 of these eclipses, and they have brought me to every single continent except for Antarctica. And I had a chance to do that, but it was only 23 seconds long, the eclipse. That wasn't worth the money or the effort in the end. But you should see that these eclipses have brought me all over the world, above the equator, below the equator, and like I said, to almost every single continent. My first one was in 1997 when I was still up at UNH. I didn't even know where Mongolia was. I had to look it up. And the ironic part is we traveled all the way there and it snowed during the eclipse, so I never even got to see it. But it was still a pretty formative moment for me. And then the next year we went rather extreme and went to Antigua, right? The total opposite of Mongolia where it was snowing. And we were successful, I believe, getting data for that one. And I'll just let you know that each one of these has a little story for me, and I have to be careful not to get too distracted. But let me see, I will be talking more specifically about the 2019 eclipse. You'll see some pictures actually a little bit later of us at these various sites, so I won't distract too much. But, you know, like in Antigua, right, it was cheaper to have us all stay on catamaran boats and have private chefs than it was to find a hotel, so that's what we did. And those were the two that I did at UNH. And then when I came to Bridgewater, I believe the first one that I saw from Bridgewater was probably the one in Zambia. And that was the first time I said to Rob, oh, by the way, so I met Rob, the blind date, right, was right after I got back from Mongolia. So I was a truly interesting person to talk to because I had this great trip to talk about. And he didn't come tonight, the one to Antigua, but in 2001, I talked him into going to Africa with me. And after that, he was completely hooked. So he's been with me to the one in Zambia and the one in South Africa. And then the one after that was in Libya, but we now had a one-year-old daughter at the time. So he stayed home and I went to Libya, and she ended up taking her first steps when I was flying home. And I called from Heathrow and he could tell me all the good news about that, which was pretty exciting. And I want to say that most of these trips, since I've been at Bridgewater, were supported by CARS, which is the Center for the Advancement of Research and Scholarship, which I believe many of the grants are supported by foundation money. And it's a great way for faculty to just get even enough money to travel to do this kind of work. So it's been really, really valuable for me. So that was my little story about 2006. I have some pictures to show you from that one. What else do I have from here? I have to keep moving my screen so I can see what pictures are here. After that was China. I brought a high school teacher with me on that one. I also brought a high school teacher with me to the Marshall Islands. The Marshall Islands was pretty exciting because that's where a lot of the atomic bomb testing has happened. And so we brought Geiger counters with us to learn about that. French Polynesia was great. Norway was the first time above the Arctic Circle for me. And I was at a site that was very close to the seed bank, which you maybe have heard of, where they store seeds from around the world in case there's an apocalypse of some sort, so that we can regrow. And there's only been one withdrawal from that seed bank so far, and that's from Syria. And Shadi is actually from Syria, and she had the opportunity. There was an eclipse visible from Syria, and I was invited to go on that, but I was trying to finish my dissertation, so I decided to do that. But she was received as a true hero coming back to lead this expedition to go see this thing. And I'm really sad I didn't go, because there's no way we could go back to Syria now. Then 2017 comes along, and all of a sudden, Haley is old enough to go on this eclipse expedition, and Rob could join us. So the two of them were with me on this expedition, and then they also joined me in 2019, along with some Bridgewater students, one of whom, Sarah, is on this call, I think, and you'll see some pictures of her later. So to sum up, right, these eclipses, this little 75-mile wide dot has brought me around the world with a group of people who we call the Solar Wind Sherpas, because we have to bring all of our equipment with us. It's very hard to ship things to remote places, so we tend to carry it as carry-on luggage, as checked luggage, and often at the sacrifice of what clothes we can bring with us on these trips. And so the Solar Wind Sherpas, right, I've got some pictures here of a few of them for you. Here is, let me switch the earliest one, I guess Zambia 2001, here we are. There's Rob, there I am with my Bridgewater State College t-shirt on. We stayed at a place called Hippo Camp because hippos would walk through our camp at night. What's next? Oh, Libya, right over here in Libya. That's there I am, and there's Shadia. We were in the middle of the desert, and the only way we could get anywhere was using Gaddafi's actually military. So we had a lot of colonels and Russian helicopters and C-130s bringing us everywhere, and that was the time when Gaddafi was behaving himself, so we were very lucky. Here we are in China. There I am, and there's Shadia, and there's the high school teacher right there that we brought. We had beautiful weather for that one. The Marshall Islands, there I am, there's Shadia. 29, see. Oh, and then Svalbard, here we are in the above the Arctic Circle. There I am, trying to represent New England, right, in my short sleeve shirt, because, you know, we're hardy people. And Shadi is right next to me right there. One little fun story about that trip is that because we were in the Arctic, some of us had to be trained to shoot polar bears in case any came nearby. So I was nominated. So I was trained on how to shoot polar bears. Thankfully, I didn't have to do that. I should probably put that on my resume if need be. And then we get to 2017, the largest group we've ever had. There's Rob with his cowboy hat. There's Haley. There am I. There were many other group pictures that we could have put on here, but I want to point out with this slide to tell you that every year the group is different. It's an international group of people. There are students, there are teachers, there are researchers, there are engineers, there are family members. And it's remarkable that the teams always manage to coalesce together and do really good science together on a decent budget. I mean, you know, we do this for a lot less money than, like I said, than launching a rocket. So, okay, let me bring you back. Let me bring you back to, I'm going to get you to the science now, right? So here's the sun, the moon, and the earth, right? And here's the spot where we stand. This is what it looks like when the umbra travels across the earth from space. And I'll let that go through a couple of times. So you notice if you're standing over here, you're not going to see the eclipse, right? And this is the shadow of the moon crossing across the earth. So now let's do it from the flip, and let's look at when you are on the ground. Here we are in Svalbard. Here's the shadow coming over our head. Here's the eclipse, and you'll see better pictures of it in a minute. You know, outside of here is the penumbra. This is the umbra that you're looking at here, and here's the other side of it. This is a GoPro stuck on the side, sped up, but that's what it looks like from the earth. And this is what a still picture looks like of an eclipse. So I'm going to pause here for a second. This is the moon. This is the upper atmosphere of the sun. That's the corona that we're looking at, okay? And remember, I answered that the sun wasn't a star because it wasn't up at night. Well, guess what? When the moon blocks the sun, it actually gets relatively dark. And in photographs in particular, you can capture stars that are up during the day. So these are stars over here, right? These little dots. It's just that the sun is so bright, it outshines everything else. So you'll see pictures like this again. But this is what an eclipse looks like when you take pictures of it from one of our sites. And light is the most important tool that astronomers have. So here I'm going to give you a tutorial on how we use light. And I want to remind folks, right, you've all probably seen rainbows in the sky. And I took this picture when I was the faculty marshal at the Bridgewater's graduation in 2019, the last one we had in person. Hopefully we'll have another one soon. But you know, the light from the sun can be broken up into a rainbow. Okay, so remember that, because, you know, first, if you look here, white light is when you take all colors of light and you add them together, you get white. It's not like crayons. When you melt all your crayons together and you get this black color, when you take light and you add it all together, you get white. So you'll hear me talk about white light images. But then if you take that white light and you break it up like a rainbow, you get a full spectrum. This is the full rainbow here, and you'll hear me talk about that. And then what we do sometimes is we look at very specific colors in the spectrum to understand what's going on. So you'll hear me talk about 3 kinds of observations we make. We make the white light, which is all the colors, the spectrum, which takes that light and spreads it apart, and then certain colors of that light, or spectral lines, that we're very, very interested in, because they tell us things about the temperature of plasmas. It tells us something about the motion of the plasmas. It tells us something about the composition. I might have said that one already. It also tells you about the magnetic fields that are present. So these are like good diagnostic tools. These are almost like blood tests, right, of the sun. So let's talk about the white light. Here's a picture of Tulin, who's about to take a white light image of the sun, or preparing to. You'll see a telescope mount here on the bottom, and she's taking basic digital cameras and attaching them to really long lenses, like small telescopes. Now, Tulin is from Turkey, but she works in Germany, and she's been part of, I think, 3 or 4 eclipse expeditions. And here's an example of the kind of image you can get from this white light experiment, right? This is from 2017. I think the first one I showed you was from 2010. 2017, you can see the stars again. This might be a planet, right? And you can see that the upper atmosphere of the sun has these interesting structures in it. You can see the backside of the moon. And the white light images play an important role to give us a sense for the general structure of the atmosphere of the sun, right? These lines that you see are actually magnetic field lines that have plasma attached to them. And I like to think of them as like when you put white Elmer's glue on a piece of white paper and then you put glitter on top of it, you can see it. So the magnetic field lines are like the Elmer's glue and the plasma is like the glitter. Okay, so the glitter makes it possible, or the plasma makes it possible for us to see the magnetic field lines on the sun. And the magnetic field is the stuff that moves plasma around. And we actually think that the magnetic field plays a really important role in this coronal heating problem. And we know it plays an important role in the solar wind things that we study. So that's a white light image. And so now what we want to do is we want to take that white light and stretch it out into a full rainbow. And the tool that we use to do that is a spectrometer. And here is Ben Bow, who was at the time a graduate student at the University of Hawaii with the spectrometer. He is now Dr. Ben Bow. He just graduated. And here's a picture of Ben and Sarah, who I think is on the call, working on assembling the spectrometer in Chile. And the kind of data that you get out of that would be, remember, spreading it out in a rainbow. And what you have to do is you have to look at a very specific region. You can only look at a slit, a very small part of the corona, right, to get the spectrum of it. So here, this red line shows you the slit on the corona, and this is the spectrum in loose description terms of the light that we're getting from that. And here, in the second image, you've got the spectrometer getting data from the top is coming from this light part, the middle is dark because that's the moon, and then the bottom part is the bottom part of the corona. And you can see that things are different, like this part of this corona looks different than this part of the corona. And this is a calibration image used. This is an image from Sarah Ariema's research that she did over the summer, which I'll talk about more over the summer and during the school year. But this is the kind of this is the light spread out into a rainbow, and then it tells us things like what elements are present and which ones are dominant and how fast they're moving and stuff like that. And before I show you the next thing, I'm going to give you a review or a tutorial on what we call those spectral lines. And just do me a favor and let's focus on iron. You know, the periodic table. When iron is neutral, when it's happy and not charged up, it has 26 electrons floating around it. And if you give enough energy, right, to an electron, like light from the sun, maybe, right, you can kick one of those electrons out or even to another level. Okay, and if you kick them out completely, we call that ionized. So that, you know, iron might not have 26 anymore, it might only have 10, right? And that tells you something about the energies available to kick these electrons out. And every element takes a different kind of energy to kick out these electrons. So the reason why I tell you this is that we look at very specific elements and their ionized state. So how many electrons have been kicked out as a diagnostic tool to give us information about temperatures in the corona of the sun. And so we look at ionized iron and argon lines. And I love using this picture because this is the instrument that's used for this. And we have to look at, we have to get all 6 of these cameras. So let me pause. This is a camera. This is a long lens, and this is a filter that says, I'm only going to allow in one kind of wavelength of light. And all 6 of these are built the same, but all 6 of them have to be looking at exactly the same place. So it's like herding cats, because the minute you move one, it moves another one. And so this is Gary, who's a phenomenal technician, trying to get these aligned. And there I am with a persistent look on my face of, why isn't this working? And it's always really frustrating, right? So I had this look on my face a lot. Of trying to get these all looking at the same place, or at least pairs of them, at the very least having pairs of them. And then, you know, the temperature changes and then they will get out of alignment and we have to, you know, readjust it again in the morning and so forth. But usually the hard work pays off. So that instrument that you just looked at a specific ion of iron. It was iron 14, which meant that 13 electrons have been stripped off, I think. And what I've done is, well, what a colleague of mine did is he took the white light image and then put on top of it the iron image, colored green. So what you can see, right, is this particular ion of iron is located here, but it's not here. And it's very dense here, but it's not very dense over here. And so looking at very specific wavelengths, it says there's a certain temperature here that's different from here, or there's a different density of this ion here than there is here. And so if you do this with multiple wavelengths, you can get a really interesting picture of the sun, if you will. So those are the kind of observations we make. And so now I'm going to talk about the most recent eclipse expedition, which was in summer of 2019, where I got to take students with me for the very first time, Bridgewater students. And 3 students here were Dan, Sarah, and Rydia. And these students were supported by National Science Foundation money, as well as an Adrian Tinsley grant for the summer work. So thank you again, Dr. Tinsley, for those opportunities for those students. And this was going to be about a 2-week trip. And there's Rob, and there's Haley, and there I am, right? And the plan was to take, Shadia planned a large group of people, again, the Sherpas, and she was going to divide us into 3 groups. One group between these 2 sites, one group in Chile, and she was going to put 2 groups in Argentina. So Chile is over here. There's very tall mountains, the Andes in the middle, and then Argentina is over here. So our plan was to fly into Santiago and then have a group go to one of these 2, a group go to one of these 2, this one, and a group go to one of these 2. And the original plan was that Sarah, Rydia, and I were going to go to Mascasine, and Dan was going to go to Rodeo. So the group was being broken into 3. And the reason why we do this, by the way, is that you know, the eclipse is traveling across the Earth like this. And if it's cloudy here, and it's clear here, and it's cloudy here, at least we get some data, right? The hope is that all 3 of the sites we choose will have clear weather. and hopefully none of them will have any clouds. But in case there are, then we have some redundancy built in, which means 3 sets of equipment for each, you know, to cover all 3 sites. And so the plan was to have 3 of us go to Mascasine. Dan was going to go to Rodeo, and there's going to be another group over here. Well, in order to get from Santiago to those 2 sites in Chile, you have to cross the mountains. And the only way that you can do that is through a tunnel. I mean, if you're driving, is through a tunnel through the mountains. And I was really looking forward to this because I was going to be driving the RV through the tunnel and down this ribbon road right here. Look at the buses. You can get a sense of scale for this, right? My mom freaked out at this thought. And I intentionally used this picture because it's summer. It was summer in North America, but it was winter in South America. So it was winter when we were going. And so there was going to be snow. I was really looking forward to this. However, Mother Nature had other plans, and she said, no way, we're going to keep snowing so that you can't drive through. So all of a sudden, we have a site in Chile that we can get to, but 2 sites in Argentina that we can't. So like the day before we were planning to go driving to these places, plans had to change. And what ended up happening was Shadia and her group went to Rodeo. Dan ended up at Cerro Tololo, and Sarah Riddy and I ended up in Mamayuca Observatory up here. So we stayed in Chile, and the group that went to Rodeo, they flew. So this was all, pun unintended, but this was all on the fly. Like they had to make airplane arrangements for next day flights and so forth, and they actually managed to do it, which was pretty remarkable. And so I mostly have pictures from Sarah, Rydia, and my group, the Mamayuca group. And we were able to find a site at Mamayuca Observatory to set up our equipment. We were right by the bathroom, which is this building here. And it didn't smell too badly, which was really good. We got that fixed. And this is a picture of our experimental setup. We bring these large tents, okay? And here's Tulin with her white light telescope. Here's Ben walking into the tent to go to the spectrometer. And back here is probably Sarah Iridia with our, what we call the narrow band, the single wavelength experiments with all 6 of those cameras, which were extremely frustrating to align again. You can see the beautiful blue skies. You can see the mountains. You can also see that we're in short sleeves. I think in the end, I personally think we had the best group, right? But we also had the best weather. I mean, it was winter there, but we could walk around in our short sleeve shirts. It was really, really quite wonderful. So bottom line is this: we had clear weather. All 3 sites had clear weather. The eclipse lasted 2 minutes and 20 seconds. Here's Sarah with our narrowband experiment. I think her enthusiasm was indicative of how we all felt. Here's the whole group in Mamayuca, right? So there's Haley, there's me. Oh, there's Rob. Yeah, he was in the picture too. We had some folks with us who could speak Spanish. There's Tulin. And this is the picture from Dan's site, where you can see that shadow band, right? Where you can see the eclipse and you can see where the shadow was. All 3 sites had great success. I had fun playing with crackers. There's the partial eclipses before and after the eclipse. And it was overall, I think, just a really great experience. And here's a picture in white light from Milos, one of the best image processors I know, of the 2019 eclipse. And you can see the moon, and you can see some stars up here. I want to point those out, right? Some magnetic field lines. So I want to I'm getting very close to the end, but I want to summarize for you the 3 eclipse pictures that you've seen so far. You saw one from 2010, one from 2017, and one from 2019. If you look at these, the corona, the atmosphere of the sun, looks different in every single one. And that is more proof that the sun is terribly dynamic. It's constantly changing. And so that's why it's important to try and observe the sun during an eclipse every time we can, because it's never the same sun at all. So here's the part where I try to talk you all into going to see a total solar eclipse, right? There is going to be one visible from New England. I know some of you are, let's say, as far out as Colorado, but those of us who are still local, right? If you look at this, this is northern New Hampshire, northern Vermont. Over here is Niagara Falls. April 8th, 2024, put it on your calendar and get yourself somewhere in this band so you can stand there and look up and see a total solar eclipse for yourself. It's totally worth it. And believe it or not, and this extends further down actually into the country as well, but believe it or not, there are places already booking for this event. They tend to sell out pretty quickly because they can be really beautiful things to go see. Now, I understand that we scheduled this talk right around November. We thought it might be nice because it does coincide with a lunar eclipse that's happening in a couple weeks. And a lunar eclipse is similar geometry to a solar eclipse, right? So you have the sun, and instead of the moon between the sun and the earth, you have the earth between the sun and the moon, okay? And so the sun in this case makes the earth cast a shadow onto the moon. And here's the umbra, which is still the term that we use in total solar eclipses, and here is called the penumbra. If you're standing in a place that can see the moon completely in the umbra, you'll see a total lunar eclipse, and otherwise you'll see a partial eclipse or a penumbral eclipse, right? And so this is what a total looks like, this is what a partial, and this is what a penumbral looks like. From Massachusetts, we will see a penumbral. It won't look red, it won't look really dark at all. You'll see sort of a little bit of a shadow happening here on the moon. And it, you know, if it's clear out, it might be nice to get some hot chocolate, put on a Snuggie, head outside and go have a look. So maybe you can say that you've seen a lunar eclipse and a solar eclipse in a couple years. So there you go. I'm here to answer any questions that you might have. And I appreciate your interest in even wanting to hear about my work.
Thank you so much, Dr. Arndt. That was excellent. I learned an incredible amount from you. And yes, I just wrote down August 24th, correct? 2024. And so
April 8th, I think. It's April 8th.
April 8th? I'm just making numbers now.
Well, let me go back. Can I go back? Ah,
Where'd I get
I'll
on?
see.
Yes.
I'll look.
There we go. I don't want to get it wrong, but I was going to say I'll book somewhere in northern Vermont. That sounds like a nice place at that time. All right, April 8th. I had the 8th of the month, not the day. All right, this is everybody just me taking notes live on camera. Thank you so much. So let's see. Well, questions start to come in. I actually have a couple of my own. I'm curious, is there any kind of research value? I know you said that the real value, or one of the real values to studying the total eclipse, is that you can see that corona and you can't see it in other types of eclipse. Is there any research value in those annular or partial solar eclipses? Are people doing work and chasing those the same way that you and the other solar wind Sherpas are chasing these total eclipses?
You know, the partial eclipses, no. The annular, I think they're sometimes they use the annular eclipse to try and study the edges of the moon a little bit, because you get backlighting of the moon. But there's not as much work done on the annular ones. There's going to be an annular eclipse, actually, I think in 2022, I think. I can look that up. I've never seen one, and I think I would love to just go be a tourist and see something like that. It's going to be visible near the Grand Canyon, so great excuse to go.
I'm now gonna plan all my vacations based off of solar events. This is great. And actually that brings me to another thing I was wondering about. How do you find out, like, obviously you could map these things out yourself. Is there a website that like somebody could go to see? I know you just said there's this one in 2024 in the US, but if somebody's willing to travel somewhere else, how would you find out a place where you might see a total eclipse if you're just a lay person?
You know, there are so many sites. I can't give you one off the top of my head, but this is what I would do. I would Google, you know, total solar eclipses. And there are sites that have them predicted all the way till like the 3000s. They have them going back in time because it's pretty easy to calculate these things. And what you will find, oh, thank you for that. What you will find is there are actual companies that are set up and designed to help people travel to go see these things. So I would Google, there's no one particular one. The greatamericaneclipse.com will help you with planning for the 2024 one though. That's a good one.
Okay, yeah, we'll be ready for that. And then Sarah, who I believe you said was one of your students, asked
yes, Sarah,
if she could link a website to help answer my question.
Good. She's up at UNH in graduate school, my alma mater.
Oh, great. There you go.
Yeah, go Sarah, go.
There you go. Thank you, Sarah. Much appreciated. I'm copying that link myself right now. Perfect. So we have a question from Janine, who also notes that she's in Florida and just watched the SpaceX Crew 1 launch from Cape Canaveral. Congrats to you, Janine. I wish I was there. And her question is indigo the same as cyan in the really
Cyan.
spectrum?
No, I think they're actually sort of separate. And you know, it's funny that cyan is used more in like in the printer world. You know, you got to get the cyan cartridge, right, for your printer, or you know, you get paints and so forth. I don't think we ever really use that term. I don't anyway. We're talking about the spectrum of light. And you know, it actually turns out that the spectrum has an infinite number of colors, right? So we tend to do Roy G. Biv, okay? But indigo, where does indigo fall? Is that a little more purplish blue?
Yeah,
Yeah, something like that. Yeah, I wouldn't call them the same, but it was really interesting is that those terms are mostly used when I think of colors with like crayons and stuff like that, or paints, or printer cartridges. And I don't know if that answered. Blue, indigo, violet. Thank you, Janine.
I think so. You did say ink color, is the cyan she was thinking of as well. So a lot of comments just saying thank you and how fascinating it was, and
good.
How much everybody enjoyed your presentation. This is great. Now I just get to ask more questions that I have, which I'm happy to do. So you said you saw that eclipse lasted over 2 minutes, right? You had the one that lasted over 2 minutes. There's one you didn't go see that was only going to be 22 seconds.
Yeah.
What's the longest eclipse? I know that's difficult to answer because it moves, so it depends where you are.
If you stand in one spot, the longest that you can generally see one is through all the geometry and the perfect stuff would be about 7.5 minutes. That's the absolute longest.
Oh, okay. Wow.
Yeah.
Before this, I might have said, "Oh, that's pretty short," but now after hearing your presentations, that sounds incredible to have 7.5 minutes of that. Okay, we're actually over time. So I'm going to ask one last question. And then, but if anybody else has any other questions, feel free to send them through, and we can always send them on to you, Dr. Arndt, and get back to people. My last question, though, is
I was trying not to talk too long, but I told you it was a possibility because I get really excited by this. So, sorry.
You did great. It was perfect. It was perfect. Yeah, and now I am too. So you've done your job. So my last question is from your experience, what was the best place, not the best eclipse, but the best place that you got to go because there was an eclipse there? What was your favorite trip? Non-eclipse related or science related, just what was the favorite place that you ended up being? I know it's a hard one. It's like picking your favorite child, I'm sure.
Yes, it is like that. And, you know, every trip is wonderful for different reasons. Maybe Mongolia because it was my first. You know, the one that kind of stands out to me the most at the moment would probably be up in Svalbard in the Arctic, because that's a place that I would not ever have the opportunity to go see ever. And it was beautiful and it was cold and it was, I mean, I went on a dog sled ride. I got to take a snowmobile to go see glaciers. I mean, it was a once in a lifetime. So I think that's the most once in a lifetime, I think, out of all of them. Yeah.
I'm very jealous. That seemed amazing.
Yeah.
So I really want to say thank you, Dr. Arndt, for joining us and presenting. I want to thank Alexis and the Alumni Office for having me as well. I love doing this. This is one of my favorite things that I get to do. And I will turn it back to you, Alexis, for some closing remarks. And thanks everybody for joining us.
Thank you so much, Rob. Thanks for facilitating today's Q&A so effortlessly as always. And to Martina for taking the time to share your expertise with us today. I really found it awesome how you've made eclipses a family affair as well.
Oh, yes.
You know, I think that definitely speaks to your love for them and for what you do. And that certainly came through in this presentation. So we appreciate you being here with us today. And I just wanted to say to our audience, if anyone does have any additional questions or would like to provide any feedback regarding this presentation, we encourage you to email us at alumni@bridgew.edu, and I can pass along the questions to Martina and get them answered.
I'm also to stay on a little longer if people want to. It's fine too.
Awesome. Yeah, I'll see if any pop up, and if they don't, if anyone thinks of any after, I'd be happy to pass them along. And then also, if folks could please consider attending our next Aluminar, which will take place a little earlier on the month on December 9th, just before the holidays. It's called Toll House Kitchen to the State House Chamber, A Cookie and Me. And it's a discussion with Kathleen Tehan, who is an alum. And the registration will open on the alumni webpage tomorrow. Additional notifications and links regarding the December Aluminar will be sent via email through our monthly newsletter and will be posted on alumni social media channels. So please look out for those. And on behalf of the entire Alumni Relations Office, we thank you for taking the time to join us today. We hope each of you enjoy the rest of your afternoon, have continued health and happiness. Have a wonderful Thanksgiving, and we look forward to seeing you at future virtual and in-person events. Thank you very much. Have a great day.
Thanks, everyone.